I said last time that I wouldn't show you the circuit diagram for the JK flip-flop, but I figured for completeness I should include it, and maybe I saw something when I printed out the final exam that made me think I should present it to you guys. But a JK flip-flop is constructed from a D flip-flop. So you have a D flip-flop here. And the inputs are let me get my head on straight here. J, K, and clock. All right, so this is the circuit for a JK flip-flop, where the let's see here, what's the state table for that? Where's the state table for this flip? Okay. So the state table is zero, unchanged, 0, 1, 1, 0, 1, 1, and that's a complement. And J is the reset and K is the set. And no, J is the set, K is the reset. So so like so. That's the state table for that. Basically, if you tie the J and K inputs together, you make a T flip-flop, which we looked at last week. Yeah, but these are a little bit more complicated and bigger on the circuitry, so they're not used very frequently. You will run into them in legacy hardware applications, but in new designs, you don't see them very often. You can get the proper functionality by using the equivalent functionality using a D flip-flop or a T flip-flop, depending on the application that you're using it for. So that is that. Everybody got that down? So we will move on to the uses of the various flip-flops other than as memory. So one use of the T flip-flop, another configuration of the T for a T flip-flop would be to use a D if a D flip-flop is wired like this with the inverted output feeding back into the D input, the clock will act as a toggle. So when this is clock goes in, say this is a 1, it'll put a 1 here, and then the clock put a 1 here and a 0 here, 0 here, and each pulse on the T line coming in will invert the outputs. This is used for frequency dividers. So you would have or Fn and you'd string them together like this. This would be your frequency of your clock would be divided by 2 with each stage in the frequency divider. So here it would be half the frequency of the frequency coming in, 1/4 of the frequency, 1/8 of the frequency at the third stage. So each stage divides it by 2. So this would be a frequency divider. And you can string it along and however many stages you want or need for your application. Another way to string together your D flip-flops, let's go ahead and put this underneath here, it would be a counter, which is in essence what this is. So this would be your bit 0. And bit 1. Bit 2. And bit 4 or 3. So this acts as a counter. Each pulse, on each pulse, you would have an increase in your binary counting. This would count up 4 bits and then recycle back to 0. But if you look at the numbers that it would be, you notice when you're counting, this first column, bit 0, and the bit 3 over here, has a frequency. Each clock cycle, it toggles between 0 and 1. At half that frequency, every 2 cycles, bit 1 will toggle and then hold that for 2 cycles and then go back to 0. Bit 2 is every 4 clock cycles. So your counter is similar to a frequency divider. So your counter will count up to, and the number of stages, 2 to the number of stages minus 1, and recycle to 0. This is commonly used in timing circuits. You have a frequency, say, 1 megahertz. You would have a say a 8-stage counter or 16-stage counter that would count up up 1 every clock cycle, and you can say at when these bits here are equal to some value, some predetermined value that you determine, it will take that long to count up to that number. So the timer counters are often used in chips to synchronize behavior or time when things should happen, that sort of thing. And it's done with this type of circuit here, where you count up to a certain point and it recycles back to 0. So in this case, it would be only count up to 15 and then recycle to 0 with the 3 stages here. So yeah. The third application of stringing D flip-flops together is creating what's called a shift register. Where you take a serial data signal and you synchronize the clocks of the D flip-flops so they all have the same clock input. You don't need the Q prime, but this would generate a shift register, create a shift register where the first bit comes in, the first bit on D, when the clock hits, it passes to the output, but not through to the next one. So you would have bit 0 come in. First clock cycle, it would move to this output, and then B1 would then B1, and then B0 here. The next clock cycle, B0 would be here, B1 would be here, and B2 would be here. And then the third clock cycle, B0, B1, B2, and B3. And you would have the bits in parallel coming from a serial signal. Now, a serial signal is like what's on a like a USB, universal serial bus. You have a clock, and you would have, say, something like this, where at the clock cycle, or at the rising edge of the clock here, you would have the 1 here. Rising edge here, you'd have a 0. Rising edge, you'd have another 1. At this rising edge, there would be a 0. This rising edge would be a 1. So when the clock goes on a rising edge, it reads the value on the data line. It reads the level there. So you read here, you read here, you read here, you read here. That's how a serial signal works. You have 2 lines. You have your data line and your clock line. In a USB, I believe there's 4 lines, data, clock, and power, 2 power lines, or something like that. I don't remember the exact protocol for the USB, but it works in the same principle. You synchronize rising edge with the data being read at a given time. So that would be 1011 encoded in a serial line. This would translate that to, this circuit here would translate that to a parallel binary number, your 1, 1, 0, 1. And then you could manipulate your binary number however you wish to manipulate that. But yeah, with the this can be easily done with JK flip-flops as well, where Q and Q prime feed into the J and K inputs of each successive stage of the serial to parallel shift register. So within a computer, within the case, as it were, most signals are in parallel because they move faster. You can transfer one one full word, usually 64 bits at a time. When you're dealing with cables outside the box of the computer, like with a mouse or a keyboard, that sort of thing, having 64 wires in a cable makes a cable really thick. So outside the box, you often use serial connections to limit the amount of cables that you're running around and outside the actual box of the computer, off the motherboard and graphics card and all that sort of stuff. So you need a way to translate from serial to parallel once you're inside the box. That's what this is used for. So just 4 lines, clock, data, and power for the typical application. But I want to say that's going to be about it for the what needs to be covered. Let me see here. Let's see here. But yeah, it's that's the basics of digital logic. We're going to have the final on Thursday at noon, I think. Thursday at noon of next week. So the 30th next week. Not next week. Next week. In the meantime, study up on the notes. Make sure your diagrams and symbols are all right. Make sure notes that are on computers or tablets are printed out for the final. You are able to use your notes. Just they need to be on paper, not on a screen. You can use the calculator for the number conversions and stuff like that. The final is comprehensive, so from number systems on up to flip-flops. Let's see here. Any other housekeeping type of stuff? I guess that would be about it. In the meantime, have a good week. See you next Thursday for the final.